Our next talk is entitled Elaboration with First-Class Implicit Function Types. Andreas Kovac will be presenting the talk.
Hello everyone, this is András Kovács and I will talk about elaboration with first-class implicit function types. In this talk, I will only give a rough overview of the paper and you can look at the paper for details. Let's explain the title of the talk a bit. First, what is elaboration? It is a translation from surface syntax to core syntax. Surface syntax is a parse representation of what programmers actually see in a source file. It is usually compact and convenient to read and write, but omits a lot of typing information, and it is not necessarily well typed. The core syntax is used internally by the compiler. It is simple, well typed, and explicitly annotated, but it is much more verbose than the surface syntax. Elaboration can include inference, desugaring, instance resolution, and other things, but this talk mostly focuses on inference. In a setting with dependent types, people often use the term elaboration instead of type inference, because inference necessarily involves term inference as well, so type inference is a bit too specific. Second, what are implicit functions? These are functions such that arguments are given by inference by default and not by the programmer. In GHC Haskell, for all types are an example. These are functions abstracting over types or other type-level data. The arguments for all abstraction are inferred by default, as here, but we can also use visible type application to fall back to explicit arguments, as here. In GHC, type-level abstraction is always implicit and value-level functions are always explicit, but this restriction is specific to GHC and it is not something fundamental. In Agda, we likewise have implicit function types, but here we are free to make any function implicit or explicit, and type abstraction is just a special case of general dependent functions. Both in GHC and Agda, implicit function types control elaboration by signaling where inferred applications should be inserted. After elaboration, implicit functions are not that important anymore, because everything is fully explicit in the core syntax. Implicit function types are first class if they can be used the same way as any other type. In GHC, with rank and types enabled, we can use an implicit function as a function argument type, and in this case type inference also works fairly well. But what if we want to use an implicit function in some other parameterized data type, such as maybe, as in this particular example? This is not really possible in current GHC. There is a language extension called impredicative types, which technically allows writing down this type, but it is deprecated and doesn't actually work in practice. There is another talk at the current ICFP which introduces a new and practically usable implementation of this language extension. As a side note, users of lens libraries may be familiar with the examples on this slide. Lenses are polymorphic functions, so they can be used in higher order functions, but if we want to store them in data structures, then we have to use some new type wrappers. What happens in Agda? Here we can use implicit function types anywhere, so this type signature is completely fine. However, elaboration is not as smart as it could be, and the next line does not elaborate. Here we have to write out an implicit lambda abstraction in order to make Agda happy. The main contribution of this talk is a general solution which figures out such insertions of implicit lambdas. At this point, some people may note that the previous Agda example is an instance of something called impredicative inference or impredicative polymorphism, which is a topic in the wider field of type inference. Indeed, the main point of this work is to provide a solution for impredicative inference. However, impredicativity means mostly orthogonal things in type theory and in the type inference literature. You can look at the paper for how exactly the two notions differ. I personally prefer to use the term impredicative in the technical type theoretic sense and talk instead about implicit functions in the context of type inference. With that said, to summarize the contributions of the current work, we have an elaboration algorithm, which supports strong inference for first-class implicit function types, or impredicative inference, and it also supports dependent types and global inference, which means that the whole module or program can be considered in inference and not just particular function applications, as in some previous works. The algorithm is also efficient, it uses no backtracking or iteration, and it actually traverses the pre-syntax exactly once. And lastly, the algorithm is a modest extension of bidirectional elaboration as implemented in Agda. Since the paper's algorithm is an extension of bidirectional elaboration, first we shall briefly talk about it, then look at its shortcomings with respect to handling first-class implicit functions, then finally look at the solution presented in the paper. Bidirectional elaboration consists of two functions defined by mutual recursion on surface syntax. Let's assume a surface expression t and a core context gamma. The purpose of elaboration is to create something in the core syntax from a surface expression. First, we have the infer function, which takes as input a core context and a surface expression, and returns a core expression together with its core type. The check function additionally takes as input an expected core type and returns a core term with that type. When the expected type of an expression is already known, we use the check function, otherwise we use infer. This is similar to bidirectional type checking, but here each function also returns a core term. Let's look at a short example for how checking works. We use an informal monadic notation as we have as side effect the possibility of failure, and we also carry around as state a context of meta variables. Here we are checking a lambda expression with a function type. So what we do is to extend the context with a variable and check the function body with the codomain type. After this, we return a well-formed lambda expression. In general, the check function tries to push types inside constructors, which is beneficial for performance of elaboration and also for the locality of error messages. In the paper, the only change the elaborator can make on the input surface syntax is that it can insert implicit lambdas and implicit applications. As we will shortly see, this implicit insertion relies crucially on the bidirectional style. We won't look at the exact rules of elaboration here and instead look at some examples. First, let's look at an example for application insertion. Assume that we have the usual polymorphic identity function and we want to infer type for id applied to the boolean true. This expression is a function application, so first we infer a type for the function involved, which is id. Then we notice that the infer type is an implicit function type, so we insert an implicit application here. First, we create a fresh meta variable named alpha, then we apply the newly elaborated id expression to it. In the following, we will name meta variables using Greek letters. Now we have a function from alpha to alpha. This is good because we started elaborating an explicit function application, and now we have an inferred explicit function type for the left subterm of the application. What remains is to check the right subterm with the function domain type. Here we don't have any specific checking rule, so we change from checking to inference and infer type bool for true. Then we unify the expected alpha type with the inferred bool type. Now we can return the whole application as elaboration output together with the bool type. In general, whenever we have a bound or defined variable name with an implicit function type, when we use the name, implicit applications are inserted for the implicit arguments. Now let's look at an example for inserting an implicit lambda. We want to check this lambda expression with the usual polymorphic identity function type. First, we notice that the expression is not an implicit lambda, but rather an explicit lambda. So the expression as it is definitely does not have the expected checking type. However, we can wrap the expression in a newly inserted implicit lambda, so that's what we are going to do. We assume the implicit argument in the typing context and check the expression with the codomain of the checking type, which happens to be an explicit function type here. Now the types match up, so the checking succeeds and we return the expression with the inserted lambda. To summarize implicit insertion, when we infer an implicit function type, we may insert an implicit application, and when we check with an implicit function type, we may insert an implicit lambda. This has a nice symmetry and it performs in a fairly convenient and intuitive way in practice. Note that we don't always perform insertion in these two cases. For example, when we check an implicit lambda with an implicit function type, there is no need to do insertion. Again, for the exact rules you can look at the paper. What can go wrong with this solution? Let's go back to the failing Agda example. We also assume that we do not have a rule for checking a constructor of the maybe type. This is not necessarily always the case, and actually the most recent version of Agda can handle this example fine, but we stick to this example for the sake of simplicity. Because we don't have a checking rule for just, we first infer a type for this expression, then unify the infer type with the given annotation. The just constructor is polymorphic, so it has an implicit type argument, and we insert an application to a fresh meta variable. Next, we have to check the lambda x expression with the unknown alpha type. This is the key point of failure. The problem is that we cannot do lambda insertion at this point because the checking type is unknown. The only thing we can do is to infer an explicit function type for the lambda xx expression, but this fails to unify with the given type annotation. Likewise, we have a dual version of this problem. When the infer type is unknown, we cannot do application insertion. The solution is to represent unknown insertions in the core theory. With metavariables, we already have the ability to represent unknown terms, so we extend this to also cover unknown insertions. We add a strictly curried function type. This is a function type such that the domain is always a record type, and currying holds by definition. Here we have an example for how currying computes for this function type. The type on the left side has an empty record type as domain. We denote the record type as rec followed by a list of types. Here the list is empty, so we get the empty record type. This function type computes to just codomain type, so the trivial function argument disappears. For another example, if the domain is a record type with two fields, the function type computes to a function type with two implicit arguments. In general, a curried function type computes to an iterated implicit function type. There are also appropriate computation rules for term constructors, which follow the rules for types. Now we can represent an unknown number of implicit arguments by putting a metavariable in the domain. We use this to improve on elaboration. Previously, unknown types always prevented implicit insertion. We change this as follows. When we check with an unknown type, we insert an unknown number of lambdas using the strictly curried function type. Concretely, we insert a strictly curried lambda, which may compute later to 0 or more implicit lambdas. Changing lambda insertion this way is easy to implement and improves inference in a large number of practically interesting cases. However, we don't enhance application insertion and leave that to future work. The reason is that unknown application insertion yields rather complex unification problems, which could be a line of research on its own. Now, the running example is elaborated without issues. In the infer type for the expression, the rec alpha stands for an unknown number of implicit arguments. Also, the unknown beta type can now depend on the argument. Then, we unify the inferred and expected types. For strictly curried functions, unification tries to match the two sides of the equation by solving curried function domains. In this case, the domain is solved to unary record, which contains a set. So unification succeeds and we get the expected elaboration output. We are nearing the end of the talk, so let's revisit this picture about elaboration to provide a summary. This picture is actually not quite correct. In practical implementations, the core syntax which is used for optimizations and further compilation is not the same as the core syntax used in elaboration. We instead have a picture like this. We use a slightly larger and more complicated core theory for the purpose of elaboration. Implicit function types provide control over implicit insertions, and metavariables allow representing unknown terms. However, this core theory is also a nice and well-behaved type theory. This is in fact a modal type theory, since metavariables and metacontexts form a so-called crisp modality, or alternatively a contextual modality. If we don't use metavariables and we only use bidirectional type checking, then inference becomes rather limited. Metavariables are the natural solution for representing unknown terms, and they are a basic ingredient in implementing more sophisticated inference. It is also important to note that if we successfully finish elaboration, all metavariables are solved, and we can also just ignore or translate away implicit function types. So the extra features don't affect downstream compilation. If we allow first-class implicit function types, that causes implicit insertion to be more dynamic and more interleaved in the elaboration algorithm. Therefore, if we want to have robust inference with first-class implicit function types, we need to represent unknown implicit insertions. Strictly curried function types provide a natural and tight representation. Additionally, strictly curried functions are a modest extension of type theory, so we still have a well-behaved and computationally adequate core theory. And like the other extra features, strictly curried functions also disappear after elaboration. My impression is that if we want to have robust impredicative inference, strictly curried functions are a basic ingredient, similarly to how metavariables are a basic ingredient for general inference. Without this basic building block, potential solutions are significantly limited in power and efficiency.
Thank you, Andreas. If you are watching this talk live, Be sure to join the Q&A session with the author if it is available in your time zone.